Hi guys, in this video we'll look at ring-forming reactions, which is a type of intramolecular reaction. And we'll also look at polymerization of alkenes. Now this follows the ring expansion page, which is where we left off in the previous lecture video. Okay, so we've seen an alkene attack H+. We've did that when an alkene reacts with like HCl or HBr, or when it reacts with an acid catalyst in the hydration reaction. But what about attacking some other type of cation? What about attacking a carbocation, which is what's stated here? Well, actually, that's what happens here. And let's take a look. If you react this diene, that is in a compound that has two alkenes, a diene, if you react it with HI, we get a reaction, but we also make this ring, a six-membered ring. And it is an addition reaction, because if you take this formula, to get this formula, you have to add HI to it. HI has been added. But we're forming a ring as well. Can we come up with a mechanism or show a mechanism for this reaction outcome? Well, just like before, we have H+. There's nothing new here yet. What's new is we have two alkenes and we need to decide which alkene is going to react first. Well, instead of two carbons to judge where we're going to leave cation, left or right, we just do that twice. Would we rather leave cation at the A, B, C, or D? And the answer is here, because a cation here would be tertiary. There would be primary, there would be secondary, there would be primary. Tertiary cation is going to be the best, and it would be formed by reaction of this alkene with the H+ to give a new H on that carbon there and carbocation here. Tertiary carbocation is the best we can envision from the two alkenes. Now we've got I- here. That could act as a nucleophile and add here and give us a carbon iodine bond. But that's not this product. So something else needs to happen. What else can happen here? What else could attack the carbocation? And the answer is this other alkene can attack. Have you ever seen an alkene attack a positive atom? Yes, we just did it up here. That happens again, but this time an alkene attacks a carbon plus, a carbocation. Can that occur here? Yes, if we redraw this, there's free rotation in all these bonds through here. If we redraw this, let's see here. There's the alkene, and then 1, 2, 3, 4. 1, 2, 3, 4. Here's the carbocation, and then that carbon has two methyls. Methyl here and methyl there. One of them has a new H. I'm not going to draw it in. But if we just do free rotation, and I'll kind of indicate like it rotated, we can envision this alkene being sort of nearby to the cation, and now the pi electrons can sort of swing out and attack it. Question, do we want to leave cation on top or bottom? The answer would be top, because top would be secondary, bottom would be primary. We swing away from the top and come down and attack that positive carbon. And that gives that bond there just formed. The carbon has two methyls, and now this carbon is positive. All right, you got the pi bond there. The pi bond swings down. Okay, here's the carbocation down here. I can do another pin. It's bonded here and it's got two methyls. Okay. This swings down. Spread these out a little bit. These electrons come down and bond to this carbon down here. Hopefully this is making sense with my very simplistic here. Here's the bond I just highlighted that was made. It used to be up here. Okay, and all that up there is connected. This swings down, and now we made this bond, leaving the upper carbon up here positive. Okay, down. So you should be able to envision that. And again, this is just an alkene attacking a positive, but it's a positive carbon, a carbocation. It's also intramolecular, internal. Now from there, how do we get home? Well, now that I minus attacks here, and that gives this product. It's just rotated. The iodine is it's 1, 2, 3 carbons away, 2 methyls. 1, 2, 3 carbons away, 2 methyls. With an iodine here, it's the same compound. And so this is an example, again, of a intramolecular ring-forming reaction via an alkene attacking a cation within the same molecule. Now, this is a very common mechanism in biochemistry, and this is actually how, if you want to look up cholesterol synthesis, how cholesterol is made in your body. Cholesterol has about 4 or 5 rings, and these rings are all made by an alkene sort of attacking a carbocation in this manner. Now, we can also make rings by other nucleophiles attacking cations within the same molecule. What type of other nucleophiles may that be? Well, like a hydroxyl group. Or later on we'll see many others, maybe amino groups. There's many examples. But for now, hydroxy groups, because that's going to be analogous to where we added alcohols to carbocations. Okay? So keep that in mind. But also, look at the synthesis of THC and think about that. An intramolecular ring-forming reaction, how might that take place? but also you want to show this mechanism. Okay, the next topic here is going to be polymerization of alkenes. And this will involve addition of an alkene to an alkene again and again and again. Let's see how this might take place. If you take this alkene, very simple alkene, what is that? That looks like 1 propene. Actually, you don't need the 1 because there's no such thing as 2 propene. So if you take propene and react it with an H plus catalyst, you can get a polymer. And the polymer can be shown like this here. Typically with polymers we show a repeating unit, and that's what I have here in parentheses. It's going to be a CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl, CH2 carbon methyl, and that continues for many, many repeating units. Millions, billions, gazillions. And that's what a polymer is. We can show some length of it and then just cut it off. But more commonly, we just show the repeating unit within parentheses, carbon, CH2 carbon methyl, and then just show an N. And the N is generic for some huge number. Now on this end, we're actually going to have an H, and that comes from the very beginning of the polymerization. And we'll see that when we do the mechanism. So let's see how we might get a repeating polymerization here. Alkene H plus. Same as usual, alkene attacks where we're going to leave cation, left or right. Well, the answer would be left, and so we pull away from the left and we get the secondary carbocation. What can attack the carbocation now? Note there's no anion here. Well, there has to be one. You can't just add in H plus. If we used HBr or HCl or HI, the anion would attack here. Okay? If you just took this with HBr, you would expect that product, and you would not expect any polymer. That would just be a simple addition, because the Br minus will add to this carbocation because it's a good nucleophile. What acids have conjugate bases that are not good nucleophiles? Well, we've already stated that, and the answer is sulfuric acid, phosphoric acid, or HF. All right. And these are the acids you would want to use here. And since the anions here will not attack, what else could attack? And their answer is, well, another alkene could attack. If we draw this, let's position this like this. Here's a second alkene. It can attack. We're going to leave cation on left or right. Well, the answer would be right. So this swings away, attacks here, and that's going to give. And we're going to have to make sure we follow everything that's bonded together here in the correct ordering. If I call this A, B, C, and I call this, let's see if this works out, A, B, C, D, E, F. Which two carbons are bonded together? Well, D is bonded to B. And so I'm going to kind of turn this around a little bit. We'll come back and do it again. H, let's see here, there's 3. I call that CBA. But now we've got bonded to B is D, and D is bonded to E, and that's bonded to F. And so this is D, E, F. And where's the carbocation now? That would be here on E. And we just made that bond. Now really I flipped this around, okay? I flipped it around so it would be more like where we're heading towards. If I come back and flip this around, we could have like this. These are the same, and that is CBA. And now this part is drawn just like that part. And now if I have this here, D, E, F, now we can see how this could just swing down, and if it did that, these two molecules would be positioned the same way they are in the resulting product, except now D is bonded to B. Okay, so those electrons, the pi bond swung down, connected D to B, leaving E without the pi bond, carbocation. So what could attack this carbocation? Well, again, there's no anion, there's no nucleophile other than the alkene, so we come in with another equivalent of the alkene. And if we take this here, position it nearby, this is going to swing out and attack like this. My lettering is not going to be just A, B, C, D straightforward. E, F, G, H, and I. So what's now bonded to E? Well, that would be G. And we have H, boom, 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 boom. Alright, this is E and F, D, you can label those. Now bonded to E is carbon, carbon, carbon. And this is G, and that's H, and that's I. And the carbocation, you see the pi bond is here, G to H. Okay? G to H, but this swung up to go make bond to E. So now G is bonded to E, and H is left with no bond, and so H is going to be the carbocation. And then I is a methyl group attached there. And we can keep going. What can attack this carbocation? Well, the same thing. We can have an alkene, and it can attack where we're going to leave cation, left to right, answers on the left, and so it attacks. And you just keep going over and over and over until somebody stops me. Please. At this point, we can go back and say, or ask, can we identify a repeating unit? Now, the H was the initial, sort of how it started, the H plus catalyst. But after that, we can recognize we have a CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl. But we can just put parentheses around one repeating unit with an N. And there it is. If we want to just present it within parentheses, we sort of say something like this: CH2 carbon methyl, CH2 carbon methyl, CH2 carbon methyl, on and on and on. And that's what we get out of this. Now, polymers tend to not be well defined in terms of finite structure. They're huge, long molecules. We do sometimes get rearrangements and other things. So there's a lot to polymer chemistry, but understanding up to this point is what we want to know now. And this is an example of a cationic polymerization. It's initiated by a cation, the H plus cation. Now, cat can be cation, but really cat here means catalyst. Now, we didn't show the catalyst reformed because we didn't sort of complete the reaction. At some point, it would need to be reformed for it actually to be a catalyst, and it probably is. If you ever take an advanced course on polymers and polymer synthesis, there'll be a lot more to dive into here. Okay, use of appropriate catalyst. That is, we want to use one where the conjugate base will not attack the cation, so instead the alkene can keep reacting with the cation. And the alkene reacts over and over and over and over. Okay. Little THC. In the next video, we'll be moving down to B. Now, A were all reactions involving a carbocation intermediate, and the electrophile was either H plus or C plus, right? H plus up to here, and then we saw where we can have a C plus as the electrophile that the alkene attacks. On both of these examples, alkene attacks a carbon plus. But we haven't attacked anything else yet. Down below, we're going to start looking at reactions without a carbocation intermediate. Now, with these reactions, we will not attack H plus. Okay, so we'll begin that on our next video, and we will pick up with the anti/transition of halogen, actually elemental halogen, to alkenes, and this will be either chlorine or bromine. And these reactions are also shown on your outline. In the section Roman numeral 2 here, and we'll start with this one here to make transdihalides. Which is the type of product shown here. Okay guys, I'll end this video here.